Dear students, in this lecture we will be continuing with our discussions on drawing the shear force and bending moment diagram. In the previous lecture, we understood what is shear force and what is bending moment, and we told that to draw the shear force and bending moment, all that we have to do is first we need to identify the regions where the loading is uniform, and in those regions we have to draw a particular section, and then we need to develop expressions for the shear force and bending moment in those sections by considering the free body diagram either to the left of the section or to the right of the section. And how do we choose the left of the section or the right of the section? Depending on the which side is having least number of forces. Okay, and we drew it for a simply supported beam with a central concentrated load. Now what we will do is we will draw it for a simply supported beam subjected to uniformly distributed loading. So if you look here, it is having uniform loading in the whole region AB. So here we only need to consider one region AB. So only one single region has to be considered. Now what we will do is we will consider a section XX at a distance small x from the point A. So the origin here is A. And now what we need to do is we can consider the free body diagram either to the left of A or to the right of A. So what we will do is let us consider the free body diagram of the region to the left of A. So as you know, the reactions here will be WL by 2. The total load is W and will be divided equally on both sides. So this will be WL by 2, and the load here would be, this would be W kilonewton per meter, and this distance would be X. Again, at the section X we have to draw the shear force and bending moment. Shear force as well as bending moment has to be drawn at this particular section X for equilibrium, and they have to follow the positive direction. So how do we draw the positive direction? So this is the sign convention for the positive directions of shear force and bending moment. And if you look here, the section now we have to consider is, we are considering this particular phase, right? So this phase is nothing but we have to take these directions, okay, as the positive ones. So what we will do is let us mark the positive. This is Vx, and this would be Mx. Okay, so these are the shear force and bending moment. Now what we need to do is we need to calculate the expressions for Vx and Mx from equilibrium. So if we consider equilibrium of this particular beam portion, so if I go for sigma Fy equal to 0, so that is WL by 2 will be in the will be positive, minus the UDL contribution will be Wx. This will be the contribution of the UDL, minus Vx equal to 0. So we can write an expression for Vx as Wx minus WL by 2. Okay, Wx minus WL by 2. This will be the expression for the shear force for the beam. Now if you look here, you will see that L is a constant, W is a constant. So this particular term WL by 2 is a constant. The term WL by 2 is going to be a constant. The only variable here is X, that is your Vx is a function of X, and you see that the variation of the shear force is linear. Okay, so which means that when you draw the shear force diagram, it is going to be a straight line. It will be a straight line because you can see that this y is equal to mx plus c, that is the expression for a straight line. So it is of that nature, therefore you know that the shear force diagram is going to be vary in a straight line fashion. Now next is we need to draw for the bending moment. Again, for the bending moment, what we will do is let us take moment about the point A equal to 0. So if we take moment about the point A equal to 0, let us assume the anti-clockwise direction as positive. Now the assumption of the positive directions are all arbitrary and you can choose depending on the cases. So now what I will do is plus mx, then minus vx into, so what we can do is, instead of taking moment about the point a equal to 0, let us take moment about the section x itself, because if we take moment about the point a, what is going to happen is the vx is going to come into the picture. So vx is a complex term, so we will have more calculations. So to avoid that, what we will do is we will not take moment about the point a, rather we will take moment about the section x itself. So what we can do is let us consider sum of the moments about the section xx equal to 0. We are taking, so the shear force is lying on the section xx and therefore it will not create a moment on the section xx. So what we are going to have is, we will have minus mx will be the moment, it is anti-clockwise. Then the moments created by this udlw, so the moment created by this udlw is, this is the udlw, it is having a length x. Okay, so the total will be wx and that is going to act at x by 2. So if you calculate the moment, it is going to be wx into x by 2. So minus mx plus wl by 2 into x minus wx into x by 2. So this is equal to 0. So if you rewrite the equation, we'll get mx is equal to wlx by 2 minus wx square by 2. So this will be the expression for the bending moment. Okay, this will be the expression for the bending moment. Again, if you look, the bending moment is having a quadratic variation. The power of the expression is 2. That is, the highest term in this is 2. So y is equal to ax square plus bx plus c is the expression for a parabola or a quadratic variation. Okay, it is having a quadratic variation, or it is having a parabolic variation. So your bending moment diagram will have a parabolic variation. Now once we have the expressions for the shear force and bending moment, now what we will do is, let us write down the expression for the shear force and bending moment. So what we are going to have is, we are going to make a tabular form. The first thing is origin. The origin is a. Next thing is, we want to represent the region, and the region that we are considering is the region, there is only one region that we have to consider. Okay, that is the region AB. Next thing we have to do is, we have to write expressions for the shear force and the bending moment. So the expression for the bending moment is WLX by 2 minus WX square by 2. This is the expression for bending moment. Similarly, the expression for shear force. The expression for shear force is Wx minus WL by 2. So this is the expression for shear force. Okay. I hope these expressions are correct. Let me just cross check them. There is a slight mistake. This expression is WL by 2 minus WX. So this is the expression. There is a slight mistake in it. Otherwise it should be okay. Alright. Now what we have to do is we need to draw the shear force and the bending moment diagram. So this is our loading. So what we have to do, this is A and this is B. To draw the shear force diagram, let us draw the shear force diagram first. First thing is looking into the shear force expression for the shear force diagram. This is of the form y is equal to mx plus c, which means it is going to be a straight line. So the first inference that we are having is it is going to be a straight line. Now what we have to do is to join it by a straight line, and it is going to be having the same slope throughout the region AB, because this expression is valid throughout the region AB. Now all we require is to join a line, we require 2 points. So what we will do is we will calculate the shear force in the region A. We know that the origin is starting at A x is equal to 0. So if you substitute, we will get it as plus WL by 2. And if you want to find shear force at B, you have to replace x is equal to L. So if you substitute in the equation, you will get it as minus WL by 2. So it is WL by 2 here, and it is minus, so we will draw it in the downward direction. So it is minus WL by 2 here. All that we have to do is join it by a straight line. This will be negative, this will be positive. So this is your shear force diagram for the beam, and this is going to come exactly at the center. Okay. Next is we need to draw the bending moment diagram. Again, we know the bending moment diagram is going to be parabolic, because from the expression it is quadratic in nature. Second degree equation y is equal to ax square plus bx plus c is a quadratic equation, or it is parabolic in nature. Again, at a equal to a, so to find a, at a x is equal to 0, if you substitute, you will get the value of ma as 0. Similarly, at b, if you substitute, you will get the value of mb also as 0. Now to calculate the bending moment at the center, if you calculate the bending moment at the center, let us call C as a center, MC. At C, x is equal to L by 2. If you substitute, you will see that it is going to come out as WL square by 4, WL square by 4 minus WL square by 8, and it is going to come out as WL square by 8. So the bending moment diagram is going to be, this will be 0, this will be 0, and at this particular point it is going to be WL square by 8. Again, this expression of WL square by 8 is the maximum bending moment for a simply supported beam subjected to UDL. This also has to be, this expression also has to be by hearted, and we know that it is positive. Okay, this bending is positive. Again, there are multiple ways in which we can interpret these results. One thing you have to understand is, in our sign convention, we have assumed that sagging moments are positive. So basically, if you want to draw the deflection of this particular beam, it means that this beam is going to deflect in a fashion like this. This will be the way in which the beam is going to deflect, and crack is going to form here. Tension is going to be at the bottom, and compression is going to be at the top. Okay, I mean, so these ideas also have to be kept parallelly in mind. So that is how we draw the shear force and bending moment diagram for a beam with UDL. Okay, this is the shear force diagram, and this is the bending moment diagram. Again, if you notice, you will see that the bending moment is maximum at the point where the shear force is 0. So if you want to calculate the maximum value of the bending moment, let us say you want to find out the location of maximum moment. So we know that how do we calculate the location and magnitude of maximum moment? There are multiple ways in which we can do it. So one of the way in which we can do it is, we know that uh, dm by dx is equal to the shear force, and also we know that the bending moment is a function of x. So if bending moment is a function of x, that function of x is going to be maximum when dm by dx is equal to 0. This means that the bending moment will be maximum when the shear force will be 0. So in this particular question, we have the expression for shear force as Vx is equal to WL by 2 minus Wx. So if we equate this to 0, we will get x is equal to L by 2. That is, the location of the maximum bending moment is x is equal to L by 2. And once you know that, you simply have to substitute x is equal to L by 2 in the expression for bending moment. The expression for bending moment was W Lx by 2 minus W x square by 2. So if you substitute x is equal to L by 2 here, you will still get the value WL square by 8. Okay, so there are numerous ways in which we can always find out the maximum bending moment. I hope the idea is clear. So with this, we stop this short lecture, and maybe we will continue and do one more problem. Let us try to consider another case regarding simply supported beam. So the next case regarding simply supported beam is simply supported beam with an eccentric or a non-central load. Okay, simply supported beam with an eccentric load. This is what we are having. This is A, this is B. Let us say the load is W, and let us say this is A, this is B, and let us call the total as L. So we know from our basic mechanics that if we have a beam like this, the reaction here will be WB by L, and the reaction here will be WA by L. This is from basic mechanics. If you don't know, you can remember it from now. You can do the calculations and see them for yourself. Now, having done this, the next thing we have to do is, if we want to draw the bending moment and shear force, first thing we have to do is we want to identify regions which are having uniform loading. So in this case, if you look, you will have two regions. One region is AC and another region is CB. So we have two regions of uniform loading. So we need to develop expressions for bending moment and shear force for the region AC as well as for the region CB. So let us take the region AC first. So for region AC, this is what we are going to do. What we will do is, let us say we will be considering a section XX at a distance X. The origin will be A, and if we are considering CB, again we will consider a section XX, and in this time we will consider the origin as B. The reasons for this we have already discussed in the first lecture when we considered a simply supported beam with a central concentrated load. So in this particular case, uh, if you look the free body diagram, which free body diagram will be considered? To the left or to the right? We will be considering the free body diagram to the left because it is having only one force there. So let us draw the free body diagram of the beam to the left of the section. So this is WB by L, and this distance is X. This is your section XX. There is no other loading. Now we have to draw the shear force and bending moment forces. Now shear force and bending moment again should follow the positive sign convention. So if you draw like this, these are the positive sign conventions. The bending moment is sagging and the shear force has to rotate the element clockwise. And which directions will be choose? So if you look, uh, this is the section. So this is the face that we are having, and that is this particular face. Okay, so if you place it here, uh, simply put it, if you take a section here, okay, if you take an element here, this is the face that is open to us where we have to draw the forces. This is the face. So if you mark the forces are going to be Vx and this will be Mx. Now expressions Vx and Mx can be found out by applying equilibrium. So let us apply equilibrium. Vx is equal to WB divided by L. So this is expression for Vx. To find an expression for Mx, let us take the moment about the section xx equal to 0. So if we take moment about the section xx equal to 0, we will get an expression for mx as mx is equal to wb into x divided by L. So this will be the expression. Okay, so this is how we develop expressions for the beams. Now what we have to do is, in a similar fashion, we have to develop expressions for the region. Yeah, now next is we have to consider the region CB. So for the region CB, again let us draw the free body diagram. This will be WA divided by L, and we are considering X from here, and if we want to draw the bending moment and the shear force diagram, now here what we will be doing is, this will be the element that we are considering, and the phase will be this. So the directions here will be, this will be our Vx and this will be our Mx. Now what we have to do is, if you write the equilibrium equations, we will get Vx is equal to minus Wa by L, and to get Mx, all we have to do is we have to take moment about the section xx equal to 0. If we do that, we will get Mx is equal to Wax by L. So that will be our second equation. So once we have developed equations for both the regions, we will tabulate them. So how do we tabulate? We have two regions. Region AC is there, region CB is there. Two regions are there. Next is we require the origin. Here the origin is A, here the origin is not C, the origin is B. We need expression for Vx. Expression for Vx was Wb by L, and here it was minus Wa by L. And we require expression for Mx. It was Wbx by L, and it was Wax by L. Okay, so this is what we are having. Now having this, let us try to draw the expressions for shear force and bending moment diagram. All right. Now if you look into shear force is a constant value, and if shear force is a constant value, what does that mean? The slope of the shear force diagram is 0. If shear force is a constant value, because A and B are constants and W is also a constant, L is also a constant, so shear force is a constant value, dV by dx will be 0. Simply put it is going to be a horizontal line. Okay, so how do we draw the shear force? The shear force at A is Wb by L. So this is the shear force at A. This is Wb divided by L, and it is positive. And this is the shear force at B. The magnitude is Wa divided by L. Okay, so this is how we join them. Now if you look into Mx, again Mx is of the form y is equal to mx plus c, which means that it is a straight line. So all we have to do is we need to find MA. At the point A, we know the origin is A, therefore x is equal to 0, MA is 0. Again at the point B, if we again substitute x is equal to 0, MB will be 0. Now we need to find MC. So MC can be found out from any of the two expressions, or you can find it from both the expression. So for example, if you are taking the expression from AC, the expression is Wx by L, and if you want to find MC, the origin is starting from A. So starting from A, if you substitute C is at a distance, X is equal to A. So if you replace that in the equation, you will get it as WAB by L. Now if you are considering the expression for the region CB, if we consider the expression for the region CB, here X is starting from the point B, and the distance till the point C is, so C is at X is equal to B. The expression for mx is WAX by L. If you replace, you will get MC as again WAB by L. These are going to be the same values. So all we have to do is, and they are also positive. So all that we got to do is draw a straight line. MA is 0, MB is 0, MC is WAB divided by L. Draw them by straight lines. Here again, one thing we have to notice is the maximum of the bending moment is coming right below the loading. Okay, the maximum of the bending moment diagram is coming right below the loading, and this is also a uh, sagging bending moment diagram. We can notice all the things that we have noticed in the previous thing, that is at the point of maximum bending moment the shear force is having a sudden change from positive to negative, that is it is going to be zero where the bending moment is maximum. So all those things can also be understood. So this is basically how we draw bending moment and shear force diagram for simply supported beams for simple loadings. Now, the advanced level, what we will be having is we will be learning how to draw it for complex load cases, wherein you have multiple loading on the span. But before we do that, what we will do is we will try to take up some more cases, wherein we will learn how to draw bending moment and shear force for a cantilever, also how to draw bending moment and shear force diagram for a overhanging beam. So after having done the simple cases, then we will take up the complex cases wherein we have multiple loadings coming on the span. So with this, we will stop our discussion on shear force and bending moment diagram for simply supported beams. We will see with another topic in the next lecture. Thank you.